For 60 years, the optical laser has defined the precision of modern industry. It provides the concentrated heat needed to slice through steel and the exact wavelength required for microscopic eye surgery. In 1960, Theodore Maiman demonstrated light could be organized into a tight, coherent beam within a synthetic ruby crystal. He had successfully mastered the photon. But using light for measurement has a limitation that no amount of engineering can fix. Photons have zero rest mass. Without mass, light is unable to experience a physical push. It passes through a gravitational field or a high-speed turn without feeling the kinetic forces that act on everything else in the universe. To measure those forces directly, researchers needed a beam made of actual mass, one that could feel and react to its physical environment. They had to take the logic of the laser and apply it to a different particle, the phonon. Sound travels through a solid lattice as a wave of kinetic energy. In quantum physics, the discrete packet of this mechanical vibration is called a phonon. To create a sound laser, or Saser, scientists mapped the three basic pieces of an optical laser onto this mechanical structure. They use an external energy source as the pump, a group of atoms to serve as the active medium, and a feedback boundary to bounce those vibrations back and forth. Early designs achieved this by layering different semiconductor materials into microscopic superlattices. The rigid boundaries between these layers acted like acoustic mirrors, trapping the phonons and amplifying them into a concentrated beam of sound. While these components proved a sound laser was possible, they introduced a conflict with the environment. Ambient heat is essentially random atomic vibration, and that background thermal noise quickly destroyed the synchronization of the phonon beam. If your laser is built out of physical vibrations, any background warmth acts like heavy static. The atoms jiggle erratically, which prevents the laser from forming a coherent wave. The solution was to isolate the active medium from its physical environment entirely, using a technique called Levitated Optomechanics. Researchers place a microscopic nanoparticle inside a vacuum chamber. Then they lock it in midair using the pressure from intersecting laser beams, which act as optical tweezers. To remove the remaining heat, they apply a technique called squeezing. By pulsing the optical tweezers to push and pull on the trapped particle at exact intervals, they actively counteract and eliminate its random thermal jitters. The billions of chaotic, wandering atoms inside that suspended particle are forced into a unified rhythm. This creates a synchronized mechanical wave so sensitive it can register forces down to a yoctonewton, a trillionth of a newton. Mastering this thermal noise produced a pristine, highly controllable beam of mass. It transformed the device into a tool capable of sensing the universe's faintest tremors. Because phonon lasers utilize actual vibrating mass, they interact directly with physical forces that light ignores. This creates a foundation for quantum compasses. By tracking physical acceleration with near-perfect accuracy, a vehicle can pinpoint its exact position anywhere on Earth without ever relying on a satellite signal or external GPS. This reaches even the hardware in your pocket. Because these lasers generate high-frequency surface acoustic waves on a microscopic scale, they can do the work of the bulky filters and oscillators in modern radios, allowing an entire 6G or 7G communication system to fit on a single chip. The phonon laser is shifting from a laboratory experiment to a practical tool. It offers unjammable navigation for drones and the high-speed processing required to handle 6G and 7G data loads. The final frontier of this technology is the quest to build the world's first graviton detector. Physicists are scaling up the system, immersing a cylindrical resonator into a bath of cryogenic superfluid helium to reach its absolute quantum ground state. If a gravitational wave passes through the Earth, it transfers exactly 1 graviton of energy to that cylinder. The resonator absorbs it, instantly converting it into a single detectable phonon. We spent the 20th century learning how to control the photon to communicate. Now, by mastering the phonon, we are building the tools to feel, measure, and finally understand the physical fabric of the universe.